Good morning to all of you. Today we will start design of digital IIR filters from analog filters. So in the previous class we have seen what is the difference between a digital filter and analog filters and how to convert a digital filter from analog filters. We have seen what is the procedure, steps involving in converting a digital analog filter to digital filter. We have seen it. Now we will see the methods available to convert analog filter to digital filter. Okay, so to design the IIR filters, there are three methods are involved to convert analog filter transfer function to digital filter transfer function. Okay, now there are three methods. First one, approximation of derivatives method. Okay, all these three methods are to convert an analog filter transfer function into a digital filter transfer function, especially for IIR filters. Second one is impulse invariant method, and last one is a bilinear transformation method. Okay, so this is a very important one from exam point of view, bilinear transformation method. Okay, and we will see one by one, each one by one we will see. And one thing you have to remember, all these three methods are used to convert analog filter transfer function to digital filter transfer function. Okay, digital filter transfer function. That is the main purpose of this. You will be given, first of all, you will be given some specifications of the filter, and after that what we have to do is we have to design the approximate filter, analog filter, and from that analog filter specifications you have to convert that analog filter to digital filter. So to convert from analog to digital filters, we have three methods, and these are the three methods. So now first one, we will start the first method of converting analog filter to digital filters. Okay, now that is approximation of derivatives method. Okay, approximation of derivatives method. So now to explain this, so we will take for any derivative of a analog signal dyt by dt, which represents some nt. Okay, so what we have to do is we have to substitute backward difference equation. To take any, see, this is the analog, in the analog domain we write like that. So in the analog domain we write so this is dy by dt at t is equal to nt. So dy by dt is a differential equation. Actually the differential equations are used to represent the analog filter differential systems. Okay, now what we do is how to convert this analog filter function into a digital filter means we have to take the backward difference equation. Okay, this is the backward difference. Here y of nt minus y of nt minus t, where t is the sampling interval. Okay, sampling interval, because we know that to convert an analog filter into digital filter, we have to sample the sequence or signal. We have to sample the signal. That is what is this t. So y of nt, suppose see, if you have a signal like this yt, converting analog to digital means substitute t is equal to nt. That is what is the digital representation, or otherwise is discrete representation of the continuous time signal. Okay, now this y of nt minus y of nt minus t, which means the backward difference, delayed pulse. Nt minus t means the sequence is delayed by some interval. Now that is divided by the average value of that. Now what we take is, whenever y of n is there, so we just y of nt is substituted by y of n. That is what we write here. So yn minus yn minus 1 by t. Now what to do is, so what is the relation between these equations, and we will see now. Suppose if you apply some sequence x of t here, some signal x of n, if it is a differentiator, then what you will get is y of t is equal to dxt by dt. Okay. This is what is the relation of means between the input and output of a differentiator, xt, and output is yt. So yt is equal to dxt by dt. And suppose see, if you apply some sequence, some signal, so suppose if you take yt here, because we have taken yt here, so yt, the differentiation of yt is dyt by dt, like this. So the meaning is, if you apply any signal at input of a differentiator, the output is a differentiated sequence. Now I will remove this. So therefore now we have a equation yt is equal, means output of the differentiator is so dyt by dt. So now if you apply Laplace transform of this, yt is equal to, so Laplace transform of this yt, suppose see, for this yt what we are getting, the output is dyt by dt. Okay, now you apply the Laplace transform on this. So what is that? So y of s and y of s is equal to, apply the Laplace transform on this output, so therefore s into y of s. Okay, so which means dyt by dt and s into y of s is a Laplace transform pair, you can say that. So therefore this is the, if you want to change a time domain to frequency domain, so we are using Laplace transform here, and what the point to understand is, so yt is a time domain signal and ys is a frequency domain signal, which means we are changing from analog time to analog frequency domain. Now but what we have to do, so we have to substitute or we have to change, so this analog filter frequency domain function into so digital domain or discrete domain. For that generally we will use a jet transform technique. The jet transform technique is, suppose see whatever the equation we have seen, that is yn minus 1 by t. Okay, this is the equation for backward difference. That's what we have seen it. Now if you observe this function and apply jet transform on this, apply jet transform on the above equation, then what happens is, and we know that, see yn yz, this is a jet transform pair yn yz, and this one yn minus 1 is a shifted sequence. So therefore how much shifted? One unit sample, one sample is shifted, n minus 1. So therefore it becomes z inverse into y of z. Okay, so see yn and yz is a jet transform pair, and from the time shifting property of the jet transform we know that yn minus 1 z inverse yn minus yz. Suppose see here, if you have a 2, you will get z power minus 2. If you have a 3, z power minus 3. Like that, what happens is, so using the time shifting property of the jet transform, we can say that whenever a sequence y of n is shifted by n units right side, so you will get a factor in the frequency domain, z power minus mg. If you have a plus here, you will get plus. Like that, so we can use it. This is the jet transform. Now what we are trying to do is, we are doing converting a time domain filter to frequency domain, time domain transfer function to frequency domain transfer function. Now use this. So y for yn, the jet transform is yz For yn minus 1, the Z transform is Z inverse yz. Okay, Z inverse yz, and divided by t is there. T divided by t is there. So therefore, you take yz common. You take yz common. So then 1 minus Z inverse divided by t. Okay, this is the useful relation. Useful relation. So yz into 1 minus Z inverse by t. Now you see here, this is, now we have to compare these two. So assume that this is the equation 1 and this is the equation 2. Now we have to compare these two. Because why we have to compare? Because this is the analog filter transfer function in the time domain and frequency domain, and this is a digital filter transfer function. Now if we compare this, in the place of ys, exactly yz is there. In the place of s, what you will have? 1 minus Z inverse by t. So therefore, if you want to convert, the point to understand is, if you want to convert a time domain filter, analog time domain filter into frequency, means digital filter. So in the analog filter, if you want to, means if the signal is analog signal, if you convert them it into frequency domain, you will get a spectrum. Same thing if you have a digital means discrete sequence, then if you convert it into digital, we will have a discrete spectrum or spectrum in the frequency domain for the corresponding digital sequence or discrete sequence. Now, so this ys represents the spectrum of yt. Okay, ys represents spectrum of yt, and this yz represents the spectrum of yn. Both are frequency domain only, ys or yz, and this is for continuous time sequence or a signal, and yz is for a discrete time sequence. That is the point here. So therefore, in the place, if you compare closely this, see ys, in the place of ys you have a yz. What is the remaining thing? So therefore s is equal to 1 minus Z inverse by t. Okay, so this is the important equation to transform S domain to Z domain. Okay, that is what we are entirely doing in this entire procedure. We are transforming a sequence, means the S variable. S is a complex Laplace means operator. So S is sigma plus j omega. We know that S is equal to sigma plus j omega, and it is equal to 1 minus Z inverse by t. Okay, where sigma is the real part, omega is the imaginary part, or the frequency. Okay, now so therefore 1 minus Z inverse by t, when S is equal to 1 minus Z inverse by t, which means converting S domain to Z domain. So what is Z domain? Z domain means, so if you have a discrete time sequence, that discrete time sequence is converted into a frequency domain. So to convert that discrete signal into frequency, we will use a Z transform. So therefore whenever S is equal to 1 minus Z inverse by t, then so we say that analog filter transfer function is converted into digital filter transfer function or digital filter representations. Now so we will proceed further how to get exactly what is Z in terms of S or S in terms of Z. I will remove this. For digital filter, suppose see if we have a suppose x of n, then differentiator, actually it is a backward difference, you take yn because we are considering, so this differentiator we will get y n minus 1, otherwise simply delay element. Okay, Z inverse. Z inverse and delay. So if you want a more delay, you can use Z power minus 2. So therefore this is the digital representation for y of n. If you have a delay, then you will get so yn minus 1. And so therefore we have already seen s is equal to 1 minus Z inverse by t. For kth order, what you will have is 1 minus so s power k z power minus 1 by t. Okay. So this is the whole power. Okay. We have to use this transfer function. Means this transformation from continuous time to this is the transform variable in the continuous domain, and this is the z is the transform variable in the so discrete domain. Now, so therefore, what we can say is, if you want to get the relation between continuous transform domain to digital transform domain, so what we have to do is we must have a relation h of z is equal to h of s at s is equal to, so what is that relation? 1 minus z inverse by t. Okay, so therefore this is the relation if you want to convert analog filter into digital filter using this derivatives method. Okay. Derivatives method. Now, so therefore whenever s is there, just to substitute 1 minus z inverse by t, then that filter is converted into a digital filter. Now we will see the continuation of this mapping S domain to Z domain. Mapping S domain to Z domain. So to map that, generally what you can write is Z is equal to 1 by 1 minus ST. Okay, this is the relation. Actually this relation you can get from the previous whatever we have seen, S is equal to, so we got that relation, right? Using that relation you can get the Z variable in terms of S. Z is equal to 1 by 1 minus ST. So using this, so we can transform or otherwise we can map so S domain variable into Z domain variable, and to get that, so we'll use like this 1 by 1 minus j omega t. So this omega is analog frequency, that's what you have to so remember here. So omega is analog frequency, analog frequency, and t is the sampling interval. However, we know that t is the sampling interval. Now we have to separate it. Z is actually, it is a complex variable. So z is equal to power r into power j theta. Right? Using that, generally we say that. So this is, we can get into real part and imaginary part. 1 by 1 minus j omega t. Okay, what I am doing is I am substituting s is equal to j omega. That's what you have to understand. So substitute s is equal to j omega. So just if you substitute that, you will get this 1 by 1 minus j omega t. T already it is there. Now, so you rationalize this 1 plus j omega t divided by 1 plus j omega t. So then what you will get is, so 1 plus j omega t divided by, so it is a plus b into a minus b in that form, a square minus b square. So a square means 1 square minus b square, actually j is there, I will write completely. So a square minus, I will write square also to avoid confusion. So therefore j omega t whole square. So it is 1 plus j omega t divided by, so 1 square means 1 only. So j omega square, j square is minus 1, we know that. So j square value is minus 1. So when that minus 1 comes out, it becomes plus 1 plus omega square t square. Okay, now you can observe this, j square is minus 1 and 1 plus j omega t divided by 1 plus j square omega square t square. So now we write that in terms of the real and imaginary parts, 1 by 1 plus omega square t square, this is the real part, plus j omega t divided by 1 plus omega square t square. Okay, so this is, so we can write, see, so this x plus jy, x plus jy. So where x is 1 by 1 plus omega square t square, y is omega t by 1 plus omega square t square. Okay, like this we can represent. So the given z in terms of the real part and imaginary part, because in the s domain we have a real axis and imaginary axis. In the z domain we have a circle. We have to map that s domain to circle. That we will see in the next class. I will stop here. We will see that transforming or mapping from s domain to z domain from this equation. We will continue it in the next class. Thank you.